Okay, we're going to move into another topic area today, and that topic area has to do with welds. And before we get started with really anything here with respect to welds, I want to go ahead and make a little confession to y'all. I am not a super big expert in the area of welds, okay? And so I wish I was a little bit more learned in this area, but this is an area that you can literally spend an entire career studying, and there's kind of no end to the depth of knowledge that you could get with respect to best practices and such that have to do with welds. So I want to kind of open with that and basically just let you know that, and for that reason, some of the recommendations that I'm going to give to you guys with respect to if you have to design something with a weld included in it, for my personal recommendations that I put out, I am going to tend to err on the side of being more conservative, because I don't want to tell you guys that something will work if I'm not pretty comfortable with it working. And having said that, there are a few things that are included as techniques in the chapter that we have for this in the book, where it actually honestly makes me a little bit uncomfortable for me to tell you to do it that way, okay? Because it's not as conservative as I would want to be, given what I know about some of the dynamics that do occur within welds. And so I want to talk through some of those things very first thing right here, so that you know why what I tend to recommend is a little different than what's in the book. And it's literally that I don't feel good about being the authority to tell you to do things in a certain way when it kind of makes me a little bit uncomfortable to do so, if that makes sense. So that's kind of where we're going to start right here. So I guess very first thing here to say, just to kind of set the groundwork, is the first thing we'll say is that the electrode that is used when you weld, and by the way, I assume most of you are somewhat comfortable with the idea of what welding is, but welding is basically melting two pieces of material together in order to form a bond, okay? That's primarily what you're doing when you weld. When you do that, it is normal, although not necessarily required, but it is normal to expect that you might add a filler material. So that's what most of us have in our mind when we think of a weld, is we think of someone melting some material to a couple of other pieces of material in order to stick them together, okay? And that's not wrong, but it is one of those things that you don't necessarily have to have the filler. There are types of welds that are done where you don't have any filler. But anyway, where I say electrode here, that's referring to the filler that goes into the weld. And when I say filler, it's basically when you put these two things together, a lot of times it's helpful to introduce new material into the connection in order to cause this melting of two pieces together to not have voids, right? You don't want to actually have there be missing material that you would have thought should have been there, so you introduce more material to make that happen. What I'm saying with that first bullet right there, the first number, is that electrode material typically is stronger than the parent material for most welds that are properly done. One of the reasons for this is that you don't want to go into a weld thinking that it is going to be a certain strength and then not have it be that strength. So there's a reason, and this is a true thing, that most of the time that's the case. Also, another thing that is usually true if a weld is done properly is that it usually involves there being extra material that ends up being deposited on the weld. And so I'll show you two examples of this real quick here. One example is, let's say this by the way would be like a butt weld, which we can kind of think of all the junior high jokes and everything. Hopefully that doesn't distract us too much. But this being a butt weld right here would basically involve there being melted material that joins this together, right in here, okay? And when we think of reinforcement, it basically means that you might leave an extra piece of, extra deposit of material that would be larger than the weld that you actually made. Okay, so that would be reinforcement that we talk about right there. This can also be done when you have something that's called a fillet weld. Okay, fillet weld is where you have two pieces of material, say something like this, and what we what we'll see in just a second when we get ready to design a weld like this, we are going to have an idealized view of how that weld is shaped, right? And we're typically going to have a 45-degree line that's drawn like this, and we have a, again, an idealized view of how that works. Whereas when you account for a certain type of reinforcement, it might mean that this weld would be bigger than what we thought it was. Or it could even, this is not usually done on purpose, but it could even bulge out like this. That's actually typically not very desirable for it to bulge out like that. Why do you think that's the case? Yeah, it creates more of a stress concentration at the end, or like at the edges of where that weld is. So you typically try to avoid that. Having said that, sometimes you see welds and it looks like it has that kind of geometry. Okay, so we have to be somewhat okay with, what we do has to be robust enough so that if the weld winds up being not quite to the level that we wanted it to be, we're still okay. All right, so those are the couple of points I'll make right there at the beginning. Other possibilities that we need to consider when we think about real welds here. One is that, it's easy to think that the material that you add as the filler material, that composes the weld that we then analyze for stress. I will say that is not something that I would count on if it was me, because it is possible that since you are melting the parent materials together in the process of doing this weld. So I'll kind of do a little picture of what this, kind of how it actually works. If you're trying to weld two pieces of material together, there is a zone in both of these pieces of material, might go like this or something. There's a zone where you literally are trying to make sure that that stuff melts for the parent material so that you get a good amount of bonding, right? They sometimes call this penetration. You want for this to penetrate into the parent material so that you get the level of bonding, and this, then you would have your added material up here. Mixing can occur for these materials, and so I personally feel better assuming that mixing will occur, and we'll see how that impacts some of our assumptions that we make here in just a moment. Okay. Another thing that I will say is heat that is applied during the welding definitely has an opportunity to change the properties of the material. All right. This can be a big effect or a small effect. One of the things that sometimes happens when people actually weld things together is that they'll get it super hot, and then they will take that weld and dump it in a bucket of water, all right, while it's super hot. What can that do? It can harden it, right? That is an actual, intentional process. It very much mirrors an intentional process that is sometimes done to harden materials. If you're not careful with that, what's the problem with a material that's too hard? It does get brittle. So there's that kind of thing that can happen. The people that I do know that are a little bit more comfortable with the specifics of welding, most of them say that they do not recommend that you quench welds whenever you make a weld. Rather, just let them cool. What can be an issue if you just do a weld? Let's say these are hard materials. Maybe they're cold drawn, or maybe they're heat treated, as in they were given some sort of hardness because they were heat treated, and then you weld. And what can happen now because you welded? Yeah, you get rid of that heat treatment that was there. Your material may have been hard beforehand, and now it doesn't have the same properties as it did before you started welding. These are real issues that actually do happen. So if you have a cold drawn material or heat treated material and you weld to it, what my recommendation is going to be is to kind of start ignoring that it ever had that strength and instead treat it as if it was more of the softer version of the same composition of material. And that's a safer way to assume that your weld will behave. Okay? So that's, I'll say this is especially important when you are talking about cold drawn, I wrote it up there, or heat treated. Okay, because cold drawing and heat treatment, gets those properties by creating certain types of internal stresses and such, and the process of welding can end up messing that up. And then lastly up here, because you have this rather chaotic process. Now, some people who are really good at welding, maybe it's less chaotic than other people who are not as good at welding, but the process of melting two pieces of material together is not necessarily a super controlled process. And so because of that, the geometry doesn't end up, glassy smooth and exactly what you thought it was going to be. And because of this, these are all motivating the idea that we probably need to err to the conservative side whenever we're designing these things. There is a little bit of material here in the book that tries to do an analysis of the stresses that are induced in a weld as a result of external loading. And it's interesting. I actually definitely recommend that you read it, but I'm not going to spend time on it here because it's not what we actually end up using. So it is interesting. It's a matter of note. But what we're going to do to try to make this conservative, I'm going to give you a few kind of pieces here that I'm going to recommend if you're designing, say, in the wild or whatever, that you basically assume. So the first one is treat all stresses, okay? Treat applied stresses as shearing stresses in the throat of the weld. Okay, let me do a quick sketch so that you have an idea of what I'm talking about there. Okay, so let's say here is a little sketch of what a weld might look like. And this is a fillet weld between two pieces of material. Okay, something like this. And okay, I'm going to sketch where this weld is located. I'm going to sketch it right here. Okay, and again, we do treat that as if it's like this 45-degree angle, and so this is how we assume the geometry is going to be. The first thing let me show up here is one of the terms that we will use when we talk about these welds is called the weld size. Okay, and the weld size is basically the length of one of these legs. Okay, so that, the variable that they use here in the book is H. Again, that whenever you hear something referred to as weld size, that's what they're talking about, is the length of one of those sides. What I'm going to show you here, though, is that we're going to treat all these applied stresses as shearing stresses in the throat of the weld being, what if you took a line that went from here up to here? And so this is not necessarily the greatest angle that I could show you here, but there's a plane, right, that goes through the weld right there. If I was going to do it not in a like an ISO view, if I was going to do it more like a side view, what you would see is if this was the weld, the throat of that fillet weld would be right here. Okay, so that's the throat. All right, and what we're saying here is that we're going to treat applied loads as if it creates shearing stresses in the throat of the weld. So the throat of the weld is typically where we're going to assume area is minimum. Okay, so that's kind of one of the reasons why we do it. We also know that the strength of materials in shear is assumed to be smaller, right? And the other thing that you'll notice here is that when you apply, let's say you apply a load this way to that piece of material relative to this piece of material, okay? And let's say you're assuming that load, let's say I take that load and divide by the area of the throat, Okay? Is that technically what's happening? It's not, but what I do in terms of making that calculation winds up over-predicting the stress in that little region, okay? And the reason for that is I'm predicting it as if the force is applied directly, and as we rotate up, it's actually, like when I say directly, I mean in direct shear, okay? And what happens is at this 45-degree angle, it's actually should be, at least theoretically, a less severe situation than assuming that that load was applied in direct shear on the throat of the weld. What if I apply something more like this, where I pull with a force on the top piece, I pull with a force this way, and I pull on the bottom piece with a force this way? Same thing, right? If we assume that that creates a shearing stress in that face right there, we are actually going to over-predict how much stress it really experiences. Okay? Which that's a conservative thing to do, is to over-predict how much stress is going to be experienced. And so anyway, I'm trying to give you a little bit of a visual picture as to why, but what it ends up doing is it kind of simplifies our life a little bit, because all of the stresses that we are going to start predicting here, as far as what I'm recommending to you, is we're going to predict shearing stresses to be whatever the applied force is divided by 0.707. Now you might go, why 0.707? This is basically 0.707 is 1 over the square root of 2, and that has to do with how big that throat is for the weld. But anyway, 0.707, I figured I'd say why that ended up being that way, times H times L, where H is, again, the size of the weld, and L is the length of the weld. Okay? L would basically be, how much length of weld you would have between two parts. All right? And this is kind of our one equation, our main equation we're going to consider whenever we're working all of these problems that we do, at least for the recommendations that I'm making to be conservative whenever you're evaluating these welds. Okay, I'll make another couple of points here. There are other points that are on pages 472 and 473 that I think it's good for you to read. I'm going to show you where my approach departs a little bit from the approach that they use for a couple of the example problems in the book. I use this equation kind of no matter what, because it's more conservative. All right? What they do sometimes in the examples in the book is they will allow there to be different material properties in the weld as there is in the parent material. I don't generally assume that because I assume that there's going to be some mixing, which means it's hard for me to nail down exactly how much of the strength you're going to have from the parent material versus how much you're going to have from the added material. So I think it's a more conservative thing to pretend as if we don't have this advantage of having electrode material in the weld. All right. So anyway, they say, estimate the strength of the deposited weld material, estimate permissible loads for the parent metals, estimate permissible load for deposited weld metal. There's all these different recommendations that they give on the bottom of page 473. I will talk about that just a little bit more here in a second, but mostly what I want to say is you can essentially use this equation for everything, and it's a conservative thing to do. Okay. The other thing that they mention on the bottom of that page 473 is that you're going to examine primary shear stresses due to external forces and secondary shear stresses due to torsional and bending moments. What does that sound like? We're not going to do that part of it today, but there's going to be a technique I'm going to show you here pretty soon that looks a lot like the bolt group technique that we did earlier, so that we can separate two different types of effects that we can have on a group of welds. All right, I think that about covers all of that. I am going to do an example problem here in just a bit, but I want to kind of scroll through and talk about some of the figures that are in this section of the book, because this is honestly one of the, I think, more important outcomes for this section than learning how to analyze anything in particular. And it's to see some of the, things like welding symbols. All right, and this is a story I tell sometimes. When I took my PE exam, I felt pretty confident on most of the questions that I answered. Like the vast majority of them I felt pretty confident about. One of the questions that I think I probably missed on there had to do with welding symbols. And the reason why is that none of my reference materials that I brought with me had this particular type of welding symbol that was on there, and it was literally a question that says, what does this welding symbol mean? And it was the entire question basically. And I think I missed that one because it's not something I was super confident and comfortable with. But they do give you some guidance here on what to think of these welding symbols. Let me actually scroll down a little bit further right here, because this figure 9.1 helps out a lot to help you know what is going on. So the first thing is where the arrow points, it actually is generally going to point to one side or the other of a joint that you put on a drawing. And that refers to where the weld is going to, it's kind of the reference side for where the weld is going to occur. So wherever the arrow is pointing to, you might see here that if there are some notes on this side of the line that I just circled right there, that means these are notes that have to do with the welds that go on that side that the arrow is pointing to. Okay? Whereas on the other side, it's the other side. Okay? So knowing, which side of the line relative to where the arrow is, that is a helpful thing. Okay? There's other things. There's a number of welds. Let me point out a couple other things. You can either have a circle here, or sometimes there's not a circle there. If there is a circle there, it means that you are going to do an all the way around weld. Okay? It means that wherever your two parts meet up with each other, you're going to do a weld all the way around the whole thing. Okay? Here's an example of what that looks like on an actual part. Okay? That is an all the way around weld. It means, wherever that interface is between the two welds, you go all the way around. There are some other symbols. All right, these little symbols like that. Those symbols mean that you're doing fillet welds. Okay. There are also these little numbers that show up here, where it says 5 right here. That is indicating a weld size. Okay. There's another thing that you can do over here. You might see the 60-200. That is referring to a pitch. So sometimes you will not have a weld along an entire seam, and instead you will have a little bit of weld and some not weld, and a little bit of weld and some not welded. And this is referring to that. And basically it says over here, staggered 60 millimeters along on 200 millimeter centers, right? So each one of those is 60 millimeters long, and they are spaced by 200. All right, so these are, these are some symbols that you can think about whenever you are looking at these things. Let's see here. Anything else I want to talk about specifically? Oh yeah, grooves. Okay, so sometimes whenever you are trying to put materials together, it makes for a stronger weld if instead of, like, for example, this was a butt weld, very much like the one that I showed you here a second ago, right? Well, typically it is possible to make a stronger connection here if instead of just butting things together and allowing penetration of the weld to go far enough to allow, full joining of these two things, it isn't uncommon for there to be both sides of the weld prepared with some sort of a way to allow the weld to go deeper into the two things that are being joined. And there's a number of ways to do that are outlined right here. You can have this happening on two sides like that. You can have just one side that's beveled to allow deeper penetration of the welding process into the two pieces that are joined together. Each of these have a name, you know, the double V or single V, the double V, single bevel, so on and so forth. But the point is, you know, you can look those up if you need them, but the point is sometimes you try to allow there to be more access to the parent material by carving the sides so that whenever you're welding it back up, you're filling it with the weld material and making for a stronger joint. Here's another example of that kind of idea, is that you can have just one side that's carved out a little bit. And then, you know, this is a symbol that indicates if you have two pieces of material and you're kind of doing a seam like that. All right, so those are some interesting pieces of information. Wanted to also talk about some various types of welds, like some various geometries of welds here. I already mentioned this, but I went ahead and put it up here as another picture. Sometimes you have reinforcement, right? That means extra material that you weren't necessarily counting on to be load-bearing, and yet it will actually help generally whenever things are bearing of loads. All right. Gives you some guidance in one of these tables. We'll use this here in just a second, but it gives you some guidance on how much stress to permit in various types of welds. So we'll use that here in just a moment. What I wanted to talk about is they have these stress concentrations listed and this is specifically for fatigue problems. We'll use that a little bit more when we do a fatigue problem. But they actually have these listed, and this is nice to talk through what are these connections. All right, so a few of them are actually, you know, already listed here. So the reinforced butt weld, that is this kind of shape that we have right up here. What is a transverse fillet weld? Okay, well, if you didn't know that, if you didn't see this carefully while you were reading, it tells you this is a transverse fillet weld. And if you want to kind of expand this out, it's basically where the weld itself is sort of aligned perpendicularly to the direction of the force that's being applied. Okay, so that's what we mean by a transverse fillet weld. What do we mean by the toe of the transverse fillet weld? Okay, well, there's a, you know, based on the picture that we see on page 473, and it gives you these stress profiles. One of the things you can determine from that is that your worst case stress typically occurs right there, and that's the toe of the weld, right? Kind of at the very deepest part of the weld. So that's the toe of that weld. The end of a parallel fillet weld. Okay, that's basically saying where you have a fillet weld like this one, the end of that weld would be like right here, or there would be another end on the other side. That's where the stress concentration is typically going to be the worst for those kinds of things. And then they have one for which they don't show a good picture. So I figured I'd draw a little picture of a T-butt joint with sharp corners. Okay. And so that would be a situation where you have a, you know, piece of material here and a piece of material here. Okay. It is a T-butt joint like that, where you would load one piece like this and one piece like this, and the weld is in here like this. Okay. So that's, you know, what we mean by a T-butt joint. All right. Any questions yet at this point? All right, so let's do a problem. We're going to weld two pieces of material together. Okay? And these two pieces of material that we're going to weld together, we are going to use a weld material given by E60. This is a, you know, kind of gives you the series of the type of material we're going to use to weld this together, as filler. It'll be a fillet weld. What size? 6 millimeter, right? So that's kind of what the symbol means, 6 millimeter weld size. What does this symbol right here mean? Okay, it means we're going all the way around. This is an interesting one for us to go all the way around. Why is that? It's not all on one side, right? In order to actually go all the way around on a piece of material like this, some of that weld, 3 sides of it is going to be up here, right up here, okay? And then one side's going to be back here, but you can still go all the way around, all right? So we're going to go all the way around with that fillet weld. Has a 40 millimeter height with a 50 millimeter width. And what we want to know is how much force can we allow. And for this first part, let me add the note. Calculate this for now. Okay, calculate using the table. And tell you what, I need to look that up real quick. There's a table in here for weld strengths. Table 9.6. Okay. And what I want to point out by doing this is not actually my recommendation for you to do all the time, right? This part A, this is not my recommendation. But I still want you to see that tables like this are available, and sometimes they are useful. Okay, so I'm showing you here that basically what this table is giving you is that if you're pretty confident that your weakest location is going to be in the weld, and if you're pretty confident that you can count on the strength of the weld metal to remain whatever it is for that electrode, then you can estimate how much force you can carry in a joint based on a table like this one for, or on 9.6 right here. Okay? What I'm doing here for part B is saying, here is what I would be more comfortable doing. Because it takes what I know of what might occur in a weld like this, and it kind of makes it the most conservative thing that I can imagine, so that it makes me more comfortable specifying something like that. Okay? So as long as we're comfortable with these two things, I want you to see using a table like this to calculate a strength of a connection, but then I'm showing you that I'd be more comfortable doing something more like part B. Okay? So, you all have this written down? Let's do part A. Okay. So, part A involves using this table 9.6. And so let me go I think I have that up here. Way up here. Here's what table 9.6 looks like. Okay. What you see here is that you have your strength level of various weld materials, okay? And what we are in this 60 series, okay? And that tells us that our allowable shearing stress in the throat, if you've got a 60 series material, is that you have a 18 KSI allowable shearing stress in the throat of the weld. Okay? What I'm about to show you here is that you don't even necessarily need to know that, because what they do in this table is they take that piece of information and they basically come up with an allowable unit force on the fillet weld. This is a number of kips per linear inch of weld. Okay? When they say linear inch, what they're talking about for that linear inch, they are talking about for the length of the weld. And what you'll notice is that they give you this equation right here that is expressed in terms of the weld size. They actually go further in the table down here and they say, what about some common weld sizes? And what do you read directly off of this? Okay, a number of kips per linear inch. And so what you do there is you just literally count up the number of linear inches that you have for your weld and multiply it by this number, and that tells you how much force you can carry. Like, super simple. For us, we have a more of a metric, more of a metric technique that we have, or metric unit system that we're using. So I'm going to say, let's pick off this 12.73H for my F value, which is given in kips per linear inch. Okay, 12.73. Okay, times H actually, and this is given in kips per linear inch. Okay, now something to note about this, they are expecting this value right here to be multiplied in as a value in inches. Okay, so what do we need to do? Okay, we need to convert that. So for us, this F is going to be equal to 12.73, okay, times this value of 6. Okay, what do I need to do to get that converted to inches? That's 6 millimeters, and there are 25.4 millimeters in an inch, right? So let me write that over to the 4 millimeters per inch. So I'm going to take that 6 and divide it by 25.4. Okay, and this ends up being in kips per linear inch. Okay, so what does that end up giving us here? 12.73 times 6 divided by 25.4. All right, so this tells me for every linear inch that I have, I've got 3.007 kips. All right, well, how many linear inches of weld do I have? Okay. Well, here's what you do, and it might seem simpler than could possibly be, but it is, right? You just look at all these different lengths, and you add them up. Okay, the reason this works to just add them up, even though they are not in the same orientation relative to each other, goes back to that assumption that we made at the very beginning, that we're going to assume we always have a shearing stress, and that shearing stress is always going to be felt in the throat. Okay, and the equation was F over 0.707 HL. Okay, we're assuming that even though that's not true, we're still assuming that the force is directly applied in the throat, and that that is basically a conservative assumption, and this allows us to sort of ignore the small change or the changes that could occur due to the fact that these are not all aligned exactly the same. All right, so what should we do with that? The total amount of force will be equal to this amount of force per linear inch. I'll just call this kips per inch here, multiplied by the total length that I have here, which is going to be 2 times 40 millimeters plus 2 times 50 millimeters. Okay, now that won't work real well the way it is right now. What else do I need to do? Okay, yeah, I need to convert this into inches, and so to do that, I need to have 1 inch is 25.4, and then, yeah, 25.4 millimeters like this. Okay, and that'll end up just giving me a value in kips. Okay, so this times 2 times 40 plus 2 times 50. Okay, and then all of this times 1 over, let's say I'll just divide by 25.4. So 21.31 kips. Now, what kind of unit system did we start the problem in? Okay, we started in a SI type of a system, metric, and now we have an answer that's given in a US system due to the data that was available to us in that table. All right, so it'd be a good idea to know how to get from here to something else. So first of all, maybe we'll know that a kip is 1,000 pounds. But then what else do we need to know? Yeah, and the number for that is available. It is 4.45. I know that because I've done this a good number of times. But if you look at table A2, page 1014, 1 pound is 4.45 newtons. Okay, so what we'll do here is do 4.45 newtons per pound. All right, and this is actually going to give you a very large number of newtons. Why? A newton's not that much, right? There's a newton, if you weighed an apple, it would weigh about a newton, right? So I'm actually going to go ahead and put another conversion in here, and that is that we have, we're going to go to kilonewtons. Okay, and when you see that, those two values of 1,000 will negate each other or cancel each other out. All right, so we take this and we multiply it by 4.45. And that gives us 94.83. kilonewtons. Okay? And just to review, what kind of assumptions were built into this calculation? We're assuming the material has what strength? The strength implied by the electrode material being the stuff that would fail, right? And that's given in that table. Remember, it was 18 KSI. Okay? That may or may not be true, that it ends up that way, but that's the assumption that we made. We also assumed there was no mixing, and so that there were a couple of assumptions that we had built into that number. Now I'm going to say I'm more comfortable with doing it like we say in part B right here. Okay. It says here, if parent material is 1015 cold drawn steel and mixing occurs of the material, okay, how much force can it carry then? All right, so let's start by looking up some values of strength for 1015 steel. I have those here, so in the interest of time, I won't go to the table and look that up. Okay. But they turn out to be that the ultimate strength for that 1015 steel is going to be 390 megapascals. 1015. And this is something I need to say about this. Okay. Actually, let's see here. Got to find my proper notes here. One of the things that happens in order to make the kind of assumption that I want to make here is you might see this is cold drawn, right? That means it's going to have strength properties that are stronger than what we can really assume that they will have once this weld occurs. I may not have written these down. So anyway, let me go ahead and grab them for a 1015 type of steel. And what we see on page 1048, table A20, okay, we can pick off a strength that we have for cold drawn, but I'm not going to use that one. I'm going to instead find the tensile strength for the hot rolled version. Why am I doing that? You can't count on the strength that was built up due to that cold drawing. You can't count on that still being around. So I'm going to pick off 340. So maybe I'll say hot rolled, right? We're going to pick off that we have S sub UT being 340 MPa. All right, and then the yield strength is 190 MPa. Okay, and I'm going to, just to really put a point on it here, this is not a mistake. Okay. Well, how do I use those? Right? Well, we got to go back up here and look at these tables so that we figure out some allowable stresses, because they do have some recommendations here. Okay. Stresses permitted by the AISC code for weld metal. Okay. And they have tension for a butt weld. That's not what we have, because we have what? More of a fillet style weld, so that's not what we're dealing with. Okay. Bearing for a butt weld, that's not what we're doing. That's basically if you have something that's more in compression. We don't have bending for this problem, so that's not it. So none of those are what we're talking about. Simple compression for a butt weld, okay? That's not what we're dealing with either. Now let's get to shear. Okay, that is what we're dealing with. And one of their recommendations is don't allow the value to go more than 0.3 of the ultimate strength. Okay? It says that, but then it also says shear stress on base metal should not exceed 0.4 times the yielding strength of the base metal. All right? So we're going to evaluate these two cases, okay, where we're going to look at a 0.3 of the ultimate strength in the throat of the weld, and then we'll look at a 0.4 of the shearing stress on the base metal. Okay, now, if we're going to actually follow kind of the guidelines I set out just a second ago, let's talk about this one right here for just a second. What they probably mean there is to use the area as if, you know, like you would use the area right here. Okay? What's more conservative than using that area? You use the throat area instead of that area, right? That's the same assumptions that we've used for everything else for that formula. You assume that throat area, it's more conservative. If you assume that the materials mix, then I would say it's probably more appropriate to use that throat area than to use the shearing stress to the base metal. Because the truth is, if you actually think about what happens in this material, there's a there's a big zone right in here where all of that material has been affected by the heat. It may have mixed. And so the most conservative thing I can think of to do here is to pretend like we're talking about that throat of the weld. All right, so those are our two values, 0.3 of the ultimate or 0.4 of the yielding strength. So let's figure out which of those is a worst case. Okay, so we'll start with if ultimate is worse. Okay, so we'll do 340 MPa. Okay, and we're going to take that and multiply it by 0.3. We're saying this is going to be equal to F over 0.707 times the weld size times the length of the weld, which is 2 times 40 millimeters plus 2 times 50 millimeters. Okay. What are the units? Down here in the denominator of this expression, I have millimeters squared. Over here, I have MPa. What's going to come out as far as my force value up here? It'll be in newtons. Okay. So, go ahead and calculate these. We have 340 times 0.3 times 0.707 times 6 times 2 times 40 plus 2 times 50. Okay, this ends up giving me 77883. Okay, that one again, remember, is in newtons. What is this in kilonewtons? 77.883. Okay, 77.883 kilonewtons. And what's the main reason that that's so much different than 94.83 kilonewtons down here? Yeah, so we're assuming here for the 94.83 that the strength of the weld maintains the strength of that electrode, whereas up here we're assuming it goes down to the strength level of the parent material. Okay? And if nothing else, this kind of gives you some bounds, right? You know you better never go higher than the 94.83 kilonewton for a joint like this, but this tells you maybe you should be careful not to go below or go above even a 77.883, but that's being pretty conservative, all right? So it gives you a window in which you feel somewhat comfortable, okay? But we haven't done another one yet. What if the recommendation that they give for yielding strength, okay? What if yielding guideline is worse? Okay, well, it works pretty much the same way. What we do there is we say S sub y. Okay, make sure we get this all correct in here. Shear stress on base metal should not exceed 0.4 of, and you know they do say this is the normal strength, right? S sub y is the normal strength for that material. Okay, so that means we can just do 190 MPa times 0.4, and again it's just going to be equal to the same expression that we had over here. All right. So the calculation looks very much similar. The only thing we change here is this goes to 190. and this goes to 0.4. Okay, and recommended here is 58,030.5, right? So this would be F would be 58 kilonewtons, 58.03. All right. And that's being pretty conservative, all right? So if you want to be really, really conservative on a joint like this, you would probably recommend no more than 58.03 kilonewtons if it's welded like that. Okay. The last couple minutes, I'll say, you know, one of the interesting things about the school that I attended, I went to Laterno University in Longview, Texas. It's one of the only welding engineering programs in the country. Maybe that's why I'm a little bit sensitive to this. So several of my friends, I studied mechanical engineering, but several of my friends studied welding engineering, and there's a lot to know. All right, it's a complicated field to get into. You know, that can, you know, at one phase it might look intimidating. On another, you know, way of looking at it, it's a great area of opportunity, right? If that's an area you want to become an expert in, then I recommend you do that. If you could become a really big expert in it, then come back here and teach it at Louisiana Tech someday, and you can do a better job of teaching this section than I do. So, with that, any questions? All right, I will see you guys next time.